I thank the Rajasthan College and its staff members for having given me this opportunity to present my talk. The topic of my talk is analytic functions, a very well-behaved function. Now, if you look at it, it is something that you must have already studied at college level or maybe at MSc, and many of you must be teaching this also. I've been told that the faculty, most of the faculty that we have, who is attending this conference or the workshop, is basically teaching at undergraduate levels. So keeping that in mind, I've tried to make it simple, but at the same time, trying to look at the beauty of many of these things. So let's just start from the beginning, how the whole thing works out. Let's look at, this is something that you all study right at BSc and maybe starting off MSc or even maybe BSc itself. But let's try to look at it. Let F be a mapping from R to R, A be in R, then F is said to be continuous at a point at A. If given epsilon positive, there exists a delta bigger than 0, so that x minus A less than delta implies fx minus f of A is less than epsilon, where F is a mapping from R to R. The similar type of relation we have for complex analysis. Let F be a mapping from C to C. Let Z0 be in C. Then F is said to be continuous at Z0. If given epsilon positive, there exists a delta bigger than 0, so that Z minus Z0 less than delta implies Fz minus f of Z0 is less than epsilon. So if you observe these two sentences, they're almost in fact the same, except for that R has been replaced by C. The point A I have replaced by Z0. X and A are replaced by Z and Z0. And that's it. And everything is the same. So for a student, from a student's point of view, it's very simple to remember it. When this was done, they remembered this result, replaced it, and that's it. But you know very well that no doubt they look exactly the same, but then there is a lot of difference between these two quantities. Even let's take one more example that you have used it many times. The differentiability. Let F from R to R, let A be in R, then F is said to be differentiable at A if limit f of A plus h minus fa over h as h tends to 0 exists, and we note this limit by f dash of Z0, f dash of A. And similarly, let F be a mapping from C to C and Z0 be in C, then F is said to be differentiable at Z0 if limit f of Z0 plus h minus f of Z0 over S as h tends to 0 exists. We denote this limit by f dash of Z0. So again, exactly the same thing. No changes except that R is replaced by C and A is replaced by Z0. Even if I can keep A, it doesn't make a difference. So they look exactly the same, but there's a lot of difference between this and this quantity. And that is what you normally tell the students. Here, for example, in this case, we are talking about h tending to 0 along h extended along two different directions, maybe from the positive side or the negative side. But once we come to this particular piece or this post definition, h tending to 0, it doesn't have to be only this direction or this direction. You know very well that it can be, because it is complex plane, so it can come from here to 0, from this side or this side. And not only that, it's not necessary that it should be a straight line. Here, of course, was just a straight line this way. Here, it could have been more complicated, quantity coming like this, and then converging to this quantity. So there are different ways in which it can come. There are infinitely many ways. So no doubt the definition is the same, looks the same, but the way of working or the analysis that you have to do has to be completely different. And this has to be explained to the students. That is not just the wordings or that we have written. There's a lot of theory behind this. So these are two results we did discuss. F is a mapping from R to R, and F is a mapping from C to C, differentiability. Similarly, the other one that we had already discussed was this, the same R to R and C to C. One question that does arise is many times, or maybe the students may even ask, so what happens? Why don't we study, or are there any books where we talk of a mapping from C to R and a mapping, say, G from R to C? Are there any books dealing with these things? And if not, then why is it not studied? So that is one of the questions that does arise. And let's try to see. In fact, we'll try to show that these results that we are talking about here are not that significant in the sense that it's quite easy to work with. So in fact, if you look into any book, there won't be any chapters dealing with these quantities. The reason will be the following. Let's look at it. Let's take a mapping F from C to R. Here we are talking about the mapping from C. The range is on the real side. Then the theorem is that either the derivative of f at z does not exist, or else f dash of z is going to be 0. So that's the result. So in this case, the answer is either derivative will not exist, or it is going to be 0. So nothing special after that. Anytime that we do, this is the only thing that we get. So that is the reason we don't study. But let's try to give a proof for this result. If the derivative of z does not exist, then there is nothing left to prove. That's it. But suppose the derivative does exist, then let's see what happens. Suppose f dash of z exists. That means this portion, limit as h tends to 0, f of z plus h minus fz over h as h tends to 0 does exist. Now, if this exists, observe h is tending to 0. And this quantity, if you look at, is from the domain, that is h is tending to 0 from in the complex plane. So it can tend to 0 from different directions. Now let's look at it. The numerator f of z plus h, this particular quantity, is the range part, that is the real number. Similarly, this number is a real number. So if h is tending to 0 from the real side, h is tending to 0 from real side, then this is real, this is real, this is real. So everything becomes real. So f dash of z is going to be real. So we'll get, so if h tends to 0 along the real axis, then the right hand side is going to be real number. And that is, therefore, f dash of z is going to be real. Next, if h tends to 0 along the imaginary axis, this part is real, this is real. Here, this is imaginary, so it may be of the form ik. So 1 over I, and 1 over I, is the minus I. So the whole expression is going to be this imaginary. So in that case, the right-hand side is imaginary. Consequently, the left-hand side is imaginary. That means to say, when h tends to 0 from the real side, the answer is real. And when it comes to 0 from the imaginary side, the answer is imaginary. And the answer is the same. It is f dash z. That means f dash z is real as well as imaginary. And the only number with this property is 0. The 0 is real as well as imaginary. So if h tends to 0 along the imaginary axis, then RHS is imaginary, and consequently f dash of z is going to be 0. So you observe that the whole theory reduces to only this much, nothing more than that. The moment I want to do any derivative, either the answer is going to be this quantity or this quantity. So nothing more is obtained, and that's why we don't concentrate on this quantity. But what happens when f is a mapping from R to C? Let's look at that as well. Next, let f be a mapping from R to C. Say f of t is equal to u of t plus iv of t. Remember, f is a mapping, so it's the parameter t I can take. The answer is going to be complex, so it will be u plus iv form. So f of t be equal to u of t plus iv of t, where u is a mapping from R to R, and R and v is a mapping from R to R. Now, So what, and f dash of t then clearly is going to be u dash t plus iv dash t. But what is this? U is a mapping from R to R, and we are talking about a derivative of the portion. So basically, what we are talking about here is the real analysis, a result from real analysis. Similarly, this is also a result from the real analysis. So what I've done is nothing special. Every time there is two numbers, the theory of a real analysis, the only thing is that I've taken the two terms, use our theory of real analysis to get the answer, and I have just superfluously added I, and that's the answer. So nothing new has been obtained. If I have studied real analysis and you're trying to work with this, use the knowledge of real analysis, get the answer, add an I, and that's it. So nothing special is obtained. And that is why this is also not studied. So thus the study reduces to the study of real analysis. So if you're working with this quantity, it is the study of real analysis with that I coming up. That's it. So conclusion of that is that thus we only concentrate on the mappings from R to R or C to C. And we observe that normally these are the two things that we study, the real analysis and the complex analysis. None of these two, and that's the reason. Now, I've said the word that continuous function, that we are talking about a real, a function that are really good. So well-behaved functions. So for that, we'll have to try to define a little about what we mean by this well-behaved. A continuous, normally, of course, it's not a precise word, but at least I prefer to call continuous functions as good function. The reason is the following, that suppose we are having some mapping which is continuous. Of course, let's take any function. And here, of course, a continuous function. While I'm trying to analyze this word Q. When it's a continuous function, and any function, the function may look like this, anything. Nothing special about it. Just an arbitrary function it may have here and then here and whatever it is, of course, here. But if say continuous function, observe, let us say this is the point domain, this point is 3, and that's the point, say 5. It's a continuous function, and you know that if it's going like this, then I know exactly, just the graph is there, then I can calculate f of 3. If there's just a gap of 1 point, I know what f of 3 is going to be. It's going to be 5. If there's a gap of just 1 point, whereas here I couldn't say anything. Here at least I can say that it is going to be just 1 point, that at f3 it is this. So I would say it's a good function. We can get at least an idea of what is happening at this point. But I would call this differentiable function a little better function than the continuous, because you know very well that if you have a graph like this with a spike at this point, this function is continuous but not differentiable at this particular point if there is a spike. However, if it was smooth, then it is differentiable. So no doubt I can get the idea of what is happening here. Here also I can get it, but I can say something more than that, that it is not only that number, but the curve that you are going to get is smooth. Here I can say how the curve is going to be. So from that particular point of view, I would call this as a better function, a smooth function, because look at it. I could have obtained some other diagram and so on. It would have been like this with that gap coming up and that being filled up. But then it is a certain spike, and the example that you normally start with is fz is equal to mod z, or fx is equal to mod x. these types of functions are continuous but not differentiable. So all that you have done. So I'm not going to go in the details of those, just the word good and better. So definitely differentiable functions are better than continuous functions. But now, next, we'll try to look at another terminology, that is your functions which are still better than the differentiable functions. And these are known as the analytic functions. So there are functions which are better than the differential functions. I call those as the analytic functions. And you know what an analytic function is? A function f is said to be analytic at a point if it is differentiable everywhere in some neighborhood of the point. So remember, when we're talking about differentiable, it is only this particular point at which I'm interested in when you're going to our two-dimensional figure, C. But once we talk about analyticity, we talk about a neighborhood. It should be not only differentiable here, it should be differentiable everywhere in that neighborhood. And in particular at this point. So definitely it is better here than differentiable, because in differentiable, only that point is where we concentrate on. But here we are concentrated not only at that point, but even in the neighborhood. And obviously, as you can see, that analyticity will imply differentiability. A differentiability will not imply analyticity. So function is said to be, of course, analytic in a domain if it is analytic at every point of the domain. So if you have some domain, and I'm saying that it is analytic in this domain, it means it is analytic at every point of that domain. A function that is analytic at every point of the complex plane is called an entire function. So that's the definition of entire function. It is still better than your analytic function. Analytic function we are restricting to a small domain, whereas here we are not restricting it at all. It is analytic in the whole of the complex plane that we call as entire function. So this will be still better function. And now let's try to look at the word well-behaved. I have still not tried to give an idea about it, but now let's try to see why I have used that word well-behaved. In fact, the whole results will be based on that word. Keep this in mind, that I am using the word well-behaved. You teach this term to all the students, Cauchy-Riemann equations. Let fz be analytic in a domain in an open set A. Let z be equal to x plus iy. Let fz, which is same as f of x plus iy, is equal to u of xy plus iv of xy. Then for every z in A, del u by del x is del v by del y. Del u by del y is minus del v by del x. So this you always teach to the students. But the question, what does this mean? Look at it from a closer point of view, a little more closer, or try to analyze this quantity. We are having two quantities, u and v. In your f, we are having these two quantities. Now, I take this rate of change. Remember, this gives the rate of change of u with respect to x. So del u by del x, when I take this quantity, this y that I'm considering here doesn't move around arbitrarily. This portion that I'm having of the two quantities, once it is moving in one particular direction, whatever it is, this quantity del v by del y is not arbitrary. It behaves or looks at this particular quantity and then moves around. So del u by del x is del v by del y. And similarly, del u by del y, once I look, your del v by del x with minus sign. Of course, it doesn't, I'm not bothered about signature. What I'm trying to emphasize is once a function is analytic, when I say that u plus iv are analytic, if this is moving in a particular direction, rate of change of this, then the rate of change of this is not arbitrary, but depends on this change. So that is why I call it as well-behaved. And if you go a little more, if you try to remember your physics, where velocity is calculated by the first derivative, dv by dt, that is rate of change, the velocity. So if you try to analyze and try to explain it to the students, it is something like say that the velocity of this with respect to x and this in the directions of x and y, they are related. They are the same. Del u by del x is del v by del y, and del u by del y is minus del v by del x. So these quantities are not arbitrarily moving around, but they are, if one of them is moving in one direction, the second is moving in the same direction in that direction, having the same value, but they are not arbitrary. So from that point of, they are well behaved. Next, we know that the validity of CR equation is necessary condition, but not sufficient. So examples you also must have studied definitely, that one of the first examples that you consider is f of z is equal to square root of x, y, for z equal to x plus y. Then the Cauchy-Riemann equations are satisfied at the origin, but the function is not differentiable at the origin. So again, if you look at it, you can again see the well-behavedness. That's your, say, domain D. Here, if you look at it, it says, if I take it at a particular point, then the rate of change del u by del x is del v by del y, and so on. Now we come to the converse. If this condition is satisfied, it means this condition is satisfied. Then it is not just enough to get the analyticity. The reason is, no doubt, this condition is satisfied. Similarly, the condition here may be satisfied. CR equation is satisfied. Here also CR equation is satisfied. But as the function is well behaved, the quantity here, there should not be a sudden change. There is a gradual change from here to here. That is, the continuity comes into picture. So that at every point that I'm talking about, it is not just some value satisfying CR and then suddenly it is changing to something else. That is not there. There is a gradual change here. That is, means if it satisfies this and the derivatives are continuous, then the function is analytic. So again, if you observe, the same well-behavedness does come into picture. So that's your definition. Or in fact, the theorem sufficient condition that you normally teach to the students. Let fz be equal to f of x plus iy, the u of xy plus iv of xy be defined in an open set A. Then at each point of A, let all the four partial derivatives exist and be continuous. That's the condition. And of course, satisfy the CR equations. Then the function is well behaved or is analytic. So just CR equation not sufficient. We require something more, namely continuity. A gradual change. Condition is satisfied, but condition is satisfied. Then it should not be arbitrary, but there should be a gradual change here. The continuity is to be maintained. Let's move on to end the theorem. Again, all these theorems I'm trying to explain in terms of your goodness of your analytic function. So let's look at the Cauchy's integral theorem. What does it say? Let Lz be analytic in a simply connected region D and gamma be a simple closed curve in D. Then integration gamma fz dz is going to be 0. So again, if you observe from the well-behavedness point of view, the integration, of course, when we were working on a real line, there was no problem. I could have integration from 0 to 2 or whatever it is. So 2 to 4, integration 0 or say 2 to 4. I could easily work it out. But now if I have some point here, say 2 plus some I and maybe 3 plus 2I, something like this. In that case, reaching from here to here is not unique direction. We can have different directions in which it reaches. So naturally, every person would be getting a different answer. But this analytic that we have here, the well-behavedness ensures that the answer that you get, whether you go along this direction or this direction, it is going to be the same. In fact, on any simple closed curve, the answer is going to be 0. This is what it says. And that you know I can break it up into two pieces. So integration over this minus the integration over this is your 0. So it's going to be this will be equal to this quantity integrations. So that we do. So again, you can see that just the differentiability would not have given us what we wanted. The differentiability had we taken would not have given, you would be getting different answers. One getting some answer here, the other getting a different answer and so on. But it is this well-behavedness of analytic functions that ensures that the two answers that you get is the same. And in fact, that is the theorem of Cauchy's integral theorem, that fz be analytic in a simply connected region D and gamma be a simple closed curve in D, then integration of gamma fz dz is 0. By the way, many times please try to keep explain to the student every time they get confused with this word, Cauchy's integral theorem and a formula. For example, if you ask a student to write the integral formula, Cauchy's integral formula, they write the result of the Cauchy's integral theorem, and you ask them to write the integral theorem, they write the formula. So it should be mentioned or made clear to the students that the formula is calculating of some value, whereas this is just the statement that we are getting here. This answer is going to be 0. That's your theorem. So let fz be analytic in a connected region D, and let gamma be a simple closed curve in D, then integration over gamma fz dz is going to be 0. A consequence of this is let f be analytic in a simply connected region D, let z1, z2 be in D, let gamma 1, gamma 2 be any piecewise differentiable arcs joining z1 to z2. So that's your z1 and that's your z2. We have a gamma 1 on this side and a gamma 2 on this side. Then integration of gamma 1 fz dz will be equal to integration over gamma 2 fz dz. And the above theorem is not true if D is not a simply connected region. There, of course, that is required. If the function is analytic everywhere, then the answer is true. This value is going to be 0. But in case there's a hole inside it, then the integration over this need not be the same as the integration over this. And obviously you can observe, because there is something happening here, that because it naturally, if it's a well-behaved function, it's like having some problem coming up here. So it's not behaving as it should. And in fact, the answer that you know is that integration of gamma e raised to I theta is a unit circle, then the integration over gamma 1 over z dz is going to be 2 pi I. So that's the result that we normally get. Of course, that can be further worked out. All that is there. But for our purpose, for it to be well behaved, I don't want any problem occurring here. Now, yes, we come to that integral formula. Let gamma be a simple closed contour in D, and let D be the region inside gamma. Let fz be analytic in D, except at a finite number of points, say A1, A2, AN in D, which are removable singularities of fz. Then for every A in A1, A2 minus this quantity, f of A is given by this particular formula. 1 over 2 pi I integration of gamma fz over z minus A dz. So we are having some region D. Gamma be a simple closed contour. That's our gamma. And D is the region inside here. The function is analytic here and on the boundary. By the way, when we say on the boundary, on a closed set, it means on a set containing the closed set, and a bigger set, open set containing the closed set. The analyticity is always defined on an open set. So it's a convention when we say that it is analytic on a closed disk, it means it is analytic on something larger than the closed disk. Okay. So here So here, this is your gamma. And there are some singularities. They are removable singularities. So for all practical purposes, these singularities can always be removed. So they don't create much of a problem. It's like saying that you're trying to move around from somewhere and there's some small, say, small ditch or whatever you want to say, which you can jump over. You don't bother about it. You say that well, the road is okay, we can just go around it or maybe jump over it and then cross over. Only when this is quite a big one or of a different nature, we take into account. The same thing happens here also. These removable singularities can always be removed. You can get another function which behaves exactly the same, which is analytic in the whole of it, and it behaves exactly the same on the remaining part here. So from that point of view, these are not important. So let it be removable singularities. Let A be any point other than this. So A is any point other than this. Then I can calculate f of A. F of A is given by 1 over 2 pi I integration of gamma fz over z minus A dz. Well, it's a very fine theorem. But now again, let's see the beauty of this particular theorem. Look at your continuous function. Now let's look at this particular quantity. It says these z, dz, and there's a z here. So that means the variable that I'm talking about here, or the z, is a quantity dealing on the curve gamma. So whatever is the formula, it is something with the points corresponding to your curve. And then of course the point A. So if you look at it, if say theoretically, I know the structure on this. It's a theoretical result, but at least if I know what is happening here on this portion, then this can be calculated. Because A, of course, Z is already there. So Z minus A I can calculate. So this part can be calculated. That means f of A can be calculated. Even if I take the point B here, for the same curve, if this is the point B, I can calculate f of B. It will be nothing but 1 over 2 pi I integration over gamma f of z over z minus b dz. Even if the point is close by, I can do it. So observe, these can be calculated if I know the structure that is here. Let's go back to your real analysis, the continuity. As long as there was a gap of just 1 point, I was able to calculate this particular point f of A. That's your A. I can calculate f of A. But in case there is a gap slightly bigger than 1 point, something like this, then if I'm asked what is your f of A, it will not be possible. We don't know what is going to happen because the curve could have, it's a continuity, so it could have been like this. It could have been like this, or it could have been a straight line, or there are infinite ways in which, so I cannot say what is happening. So because it is reasonably good function, so only at 1 point I can see. But whereas here, if you observe, I can calculate any point in this particular piece, provided I know what is happening here, which was not possible here. And that is why I call this as a very well-behaved function. Theoretically, it's like saying, yeah, here, your rocket is going around a universe, and I know exactly what is happening here in the universe. And I want to calculate f of this sun, let's say here. I can calculate. F of the earth, I can calculate. Or anything that I want the galaxy, anything. As long as I know if the function is analytic and I know exactly what is happening at this stage, no matter how far it is. And that is why I call it a very well-behaved function. No matter what it is, I'm able to calculate, which I could not in these cases. In fact, none of the cases, even in differentiability, I could not. But it is the analytic function And this particular theorem, which says that I can calculate f of a at any point that I want to calculate, provided I know something here. What is the formula? That is immediate. The thing is, because it is well behaved, there is some way I can calculate. And that's why I call it well behaved. There are other results that I'll be talking about, maybe because the time is almost over. So I'll be continuing from here tomorrow, and we'll stop here and continue tomorrow from here on after Cauchy's integral formula and see how well several other examples I'll be giving just to justify that analytic functions are really well-behaved functions.